Good afternoon, students. Today's session, we will see the topic strain energy. So, when a body is strained, energy is absorbed in the body. This energy, which is absorbed in the body due to the straining effect, is called as strain energy. So if your body is like this, you are applying a load. So what happens? Strain will be created, and due to this straining effect, energy is absorbed in the body. So this energy is called as strain energy. The strain energy or the straining effect, may be due to a gradually applied load. Maybe due to a gradually applied load or a suddenly applied load or a load with impact or a shear stress. So before going into the following four categories, we shall see the commonly used terms. The first is resilience. So this resilience is the total strain energy stored in your body. The resilience is the total strain energy stored in your body. Second, proof resilience. This proof resilience is the maximum strain energy stored in your body. Maximum strain energy stored in your body without permanent deformation. Without permanent deformation. So when the permanent deformation happens, if it goes above the elastic limit, you can expect permanent deformation. Next is the modulus of resilience. Modulus of resilience. The modulus of resilience is the ratio of proof resilience divided by the volume of the body. So what is proof resilience? Proof resilience is the maximum strain energy stored in your body without plastic deformation. So without plastic deformation means it is up to the elastic limit. So first we shall see the derivation of the strain energy stored in body. The strain energy stored in body due to a gradually applied load. See, your body is like this, you are applying a force. What happens? There may be a straining effect, and due to this, the body gets deformed like this. So, if the body is in this position, so in the position 2, what happens is some amount of energy is stored in body. So, this energy you have to calculate. So, strain energy stored in body, it is denoted by the letter capital U. So this U you have to find. What is the strain energy stored in body? So this strain energy stored in body is equal to the work done by the load. So this is your load. So work done by the load is equal to if you draw the load and extension diagram, see this is your load and this is your extension. If you draw the load and extension diagram, your graph will be like this. So on the y-axis I am having load and on the x-axis I am having extension. So this is your load and this is your extension. For a gradually applied load, what happens? The initial value is 0 and this load goes on increasing. So work done by load is equal to the area of this triangle. So the work done by the load, you can take this as the area of this load. So what is the area of the load? So area of this triangle. Area of this triangle is equal to half. So this one is P. P into this X. Half length into breadth is the area of the triangle. So in this side I am having P and in this side I am having X. So the area of the triangle is half P into X. So work done by the load is equal to the area of triangle in the load extension diagram. So U is equal to half. We know that stress is equal to force by area. So force or load is given by stress into area. So instead of the load, you substitute as stress into area. And extension. We know that the change in length by original length is the strain. Also the strain is given by stress by Young's modulus, or I can say like this: change in length is equal to stress into the original length divided by the Young's modulus. Instead of this change in length, I am saying the extension x. So to easily understand, I am taking x as the extension or change in length. So instead of x, I have to substitute stress into length divided by the Young's modulus. So finally, I'll be getting half sigma square A into L divided by E. The product of A into L is the volume of the body. So strain energy is given by 1 by 2E into sigma square V. So this is the strain energy stored in body when you are applying a gradual load. Next, proof resilience has to be calculated. So what is proof resilience? Proof resilience is the maximum strain energy stored in your body. So how you can calculate the maximum strain energy? The maximum strain energy can be calculated when the body is stressed up to the elastic limit. So instead of this stress value, I have to substitute the stress value at elastic limit. So this is your proof resilience. And next is modulus of resilience. The formula for the modulus of resilience is proof resilience divided by volume of the body. So what is your proof resilience? It is 1 by 2E into sigma square V. So this is your proof resilience. So this stress is the stress at elastic limit, and the volume of the body is taken as V. So when you cancel volume on the numerator and denominator, you'll be getting the modulus of resilience as 1 by 2E into sigma square So we have find what is the strain energy, what is the proof resilience, and what is the modulus of resilience. For these three terms, we have calculated the formula. Next is we are going to derive the strain energy stored in a body due to a suddenly applied load. Strain energy stored in a body due to a suddenly applied load. See, if the load is applied gradually, you can have the load extension diagram like this. So this is the load extension diagram for a gradually applied load. But if the load is applied suddenly, the load is constant throughout the process of deformation. So if you draw the diagram, that is the load extension diagram, you will have a figure like this. So this is your load and this is your extension X. So this area you have to find. So strain energy stored in a body is given by the work done by the body. So work done by the body is equal to the area of the figure. So you take this as O, A, B, C. Area of the figure O, A, B, C. So what is the area of the figure? It is a rectangular in shape. So I am multiplying breadth and height. So I will be getting P into X. Strain energy is equal to load into extension. But we know that the strain energy is equal to sigma square V by 2E. So this value is equal to P into X. So what is V? V is area into length. And what is the extension X? Previously, for the gradually applied load, we have shown that X is equal to sigma L by E. So this value I have to substitute here. So instead of X, I am substituting sigma L by E. So I am taking small l itself. So if you take capital L, you can take capital L on both sides. So in the previous slide also, so here also small l is only used. So make sure that you use only the same notations throughout the equation. Either you can use capital L or small l, but it has to be same throughout the derivation. Okay. So the length and length gets cancelled, and here is one sigma, and here sigma square is there. So one sigma gets cancelled. The denominator I am having Young's modulus C, so that also gets cancelled. The remaining is sigma A by 2 is equal to P, or I can write like this: stress is equal to 2 times the load divided by area. So what can be inferred from this equation? So the stress due to a suddenly applied load. So this stress is due to a suddenly applied load. So this stress is equal to 2 times load by area. So what is this load by area? This load by area is the stress when the load is applied gradually. So the same load you are applying suddenly, what happens? It becomes 2 times so the same load that is applied suddenly. Then what happens is the stress due to a suddenly applied load is 2 times the stress applied when the same load is applied gradually. Now the third one is the strain energy stored in a body due to a shear stress. The strain energy stored in a body due to shear stress. For understanding this, you consider a figure like this, which is fixed at the bottom, and you are applying a pulling force from left to right. So what happens is the body gets deformed, and the final position will be like this. So the strain is indicated by the angle pi, and this is the height h. You take this as AB, CD, and this one as C1, D1. So before deformation, your body shape was AB, CD, and after the force is applied, the body coordinates are A, B, C1, and D1. So from D2, it has moved to D1, and from C2, it has moved to C1. So in this case, the strain energy stored in the body is equal to the work done by the load. So the work done by the load is equal to the average load into distance. So average load means since the load is applied gradually, initially you will be having a zero load. From zero load to your load value is P. So it is applied gradually. So if you take the average of these values 0 and P, you will be having 0 plus P divided by 2. So this is your average load. So P by 2 into distance. So through a distance of CC1. So this is your distance CC1. So this distance it has moved. So CC1 is equal to D1. So half, we know that stress is equal to force by area. So in this case, shear stress will be acting. So the load P is given by stress into area. Instead of the load, I am writing as stress into area and C1. Okay. So now what is the area? So this area has to be calculated. So this area has to be calculated like this. See, initially the body shape is like this. In the above figure, I have drawn only the 2D. Here I am drawing a 3D figure. So this is your height and this is your length and this is your breadth. So during the shearing process, what happens is this area will try to shear. So for calculating the area, you have to take this area, that is the length into breadth. So for area, I have to consider length into breadth. And for CC1, what is this CC1? This CC1 is the side of this triangle. If you take the triangle BCC1, BCC1, in this triangle, tan pi is equal to opposite by adjacent. So this is your opposite side and this is your adjacent side. So opposite side is CC1 divided by BC. So if the angle is very small, you can say this tan pi is equal to pi. So pi is equal to CC1 by BC. So I can write like this: pi is equal to CC1 by BC. From this, find what is CC1. So CC1 is equal to pi into BC. So what is BC? BC is the height. So instead of BC, I am substituting the height h. So now strain energy is equal to half into shear stress into length into breadth into pi into h. So this length into breadth into height is the volume of the body. So strain energy is equal to, any doubts? So strain energy is equal to half into stress into pi into volume. Also, we know that shear stress by shear strain is equal to the rigidity modulus, or the shear strain is equal to shear stress by rigidity modulus. So I have to substitute this value here. So the above equation becomes half tau into tau by g into v. shear strain is strain energy. So U is the strain energy. Strain energy U is equal to of tau square V divided by G. So the final equation is the strain energy is equal to tau square V by 2G. So this is the strain energy stored in a body when it is subjected to a shear force.